Hello, this is question 2 from the 2019 MAT. For k, a positive integer, we define the polynomial p subscript k of x as this thing, denoting the coefficients as a0 up to an. Right, so they've got all of these brackets. So 1 plus x squared, 1 plus x cubed, right, multiplied all those together to get a big polynomial of degree capital N. Part 1. Write down a degree n in terms of k. So degree n is going to be getting all of our x terms multiplied together. So we've got x times x squared times x cubed times x to the 4, etc., all up to x to the k. So we're adding those powers. So we've got triangular numbers. So the kth triangular number is what we've got there, isn't it? So we've got that n is going to be k times k plus 1 over 2, because that is our kth triangular number. Right, by setting x equal to 1 or otherwise, explain why we've got this thing for a max, which denotes the largest of the coefficients. Well, let's follow their suggestion then. So we put x equal to 1, so we're going to get 2 times 2 times 2 times 2, and we're doing that k times. So we've got 2 to the k on the left hand side, and that's going to be equal to a0 plus a1 plus a2 plus all the way up to an. Right, so we've got that. Well, yeah, that's going to drop out, isn't it? Because we've got n plus 1 coefficients. That's why they got that n plus 1 on the bottom. So we've got n plus 1 coefficients adding up to 2 to the k. So the a max must be greater than or equal to the average coefficient, and the average coefficient is equal to 2 to the power k divided by n plus 1. So we've got a max is greater than or equal to 2 to the k divided by n plus 1. Right. Fix I greater than equal to 0. Explain why the value of AI eventually becomes constant as k increases. Okay, right, fix I greater than equal to 0. Value AI. So one of these coefficients eventually, right, let's look at an example, because I can't visualize this at the moment. So say, well, let's take I is equal to 1. That's not 0, seems a bit dull. So let's say I is equal to 1. So as we increase things then, so if k is, what are we trying to do here? Okay, let's start with, well, let's say k is 1 as well. I don't know. So we've got I is 1, k is 1. So we're just doing the first bracket. So we get 1 plus x, which means that AI is equal to 1. If k is equal to 2, then we're getting 1 plus x times 1 plus x squared, and we're just getting x again. So that's also equal to 1. Right. So what if we've done k? K can be, what do I want to do on this? I mean, I suppose we could have 0 in there, but maybe I as 1 isn't that useful. So what's actually happening here? Because we're multiplying these out, but we want to get the coefficient of just x. So we can't include the x squared term. Yeah, that's going to be what it is, isn't it? So yeah, say we had I is equal to 2 and we had k is equal to 1. Then we've got 1 plus x, which means that a2 is equal to 0. Then we do k is 2. So we're getting 1 plus x times 1 plus x squared, which means that we're getting the a2. So we want the squared term. So that's going to be 1. Then we do k is 3. 1 plus x squared, 1 plus x cubed. But the only way we're going to get x squared out of this, again, is doing the 1 times the x squared. these, when we do extra powers, this just can't help. We can't get any more out of it. So, although if we had cubed, then we could do the x times x squared would give us a cubed. But then once we've gone past the x cubed term here and put x to the 4 in, we're not adding any more on. Right, so yeah, that's what it's going to be then. So how do we actually put this into words? The key part of this then is when we reach that k is I, then we're kind of set then, aren't we? I think so. When k is greater than I, we are what are we talking about then? The x to the k terms cannot contribute to I because the power is too high. Because power is too high. So therefore we're getting a constant. So therefore AI tends to constant. Right. Yes. Yeah, it took a while to unpick it. Again, it's another one of those ones where I couldn't really visualize it until I actually started writing it out. And then you can start seeing, yeah, if you're looking for the x squared coefficient, then adding in a 1 plus x cubed isn't going to help, because you're either just doing 1 times everything that you've done before, or you're doing an x cubed but multiplied by it all. And if you're multiplying by x cubed, well, it can't be in the x squared coefficient. So yeah, it doesn't make any difference when you're going beyond the power that you're actually interested in. So that is that one, right? That was quite sneaky. Let's get a fresh sheet up then. The student correctly calculates for k equals 6 that is P6. Well, okay, that couldn't have been much fun going through that. On the basis of this calculation, the student guesses that AI equals AN minus I. For I is between 0 and n inclusive. So AI equals ANI. So the coefficients are the same whatever end you start at. So 1, 1, 1, 2, 2, 3, 1, 1, 1, 2, 2, 3. Yeah, so it doesn't matter if we start at this end or this end. We're getting the same list of coefficients. By substituting x minus 1, x to the power of minus 1, so 1 over x for x, or otherwise, well, I'm not going to do or otherwise, show that the student's guess is correct. Okay, so let's give this a bash then. So let's put in x to the minus 1 in all of this. So we've got 1 plus x to the minus 1. And 1 plus x to the minus 2. And this is going to keep on going up to 1 plus x to the minus k. And then that is going to be equal to a0 plus a1 x to the minus 1 plus dot 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 plus an x to the, where am I, minus n. Right, that's that. So let's put x to the minus 1 in. And how am I going to make this? We need to have something that is then showing that we're trying to pair these things up, aren't we? So we're trying to pair up A0 and AN. So we're trying to pair those, and then A1 with AN minus 1. So we need to get those things linked in some way. So how on earth am I going to do that? We've got all of this thing, and we're comparing it to, let's write the other one underneath. So 1 plus x squared dot 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 1 plus x to the k, and then that's a0 plus a1 x plus dot 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 an x to the n. And we want to pair up the first one and the last one in these things. So we want to get this a0 here and this an there being the same in some way. So that suggests multiplying by x to the n, because then at least they'll be standing on their own. So let's take this one and multiply it by x to the power of n. Eesh. Okay, let's not worry about the what on earth is going to happen to the left hand side. Right, let's do the right hand side first, because we're going to get a0 x to the n plus a1 x to the n minus 1 plus dot 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 plus an at the end, which suggests then that we're going to get exactly the same, that is going to turn our left hand side into the original left hand side when we do this. So x to the n, let's just think through what x to the n is again. So x to the n is multiplying all of the x powers together. So x to the n is, yes, okay, right. So x to the n is equal to x times x squared times x cubed times x to the 4 all the way up to x to the k. That's what we've done to get x to the n. So if we, when we multiply the left hand side by all of this, we can take that x and multiply the first bracket by x. We can take the x squared and multiply the second bracket by x squared. So we're going to end up getting x plus 1, x squared plus 1, dot 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 dot, x to the k plus 1. So these are now identical. So we can now, so that's equation 2, that's equation 3. So you can say, okay, well, let's compare 2 and 3. Left-hand sides are the same. And then compare coefficients, which means that we're getting that a0 is equal to an, a1 is equal to an minus 1, etc., which is this thing. So ai equals an minus I. Right, that was not easy, but at least they told us what to do of subbing in that first bit, so it gave us that first equation. But yeah, doing this bit, I suppose, multiplying by x to the n, required a little bit of a jump, I suppose. But that's the thing, when we know we're trying to get these together, they've given us the answer that we're looking for, what we're trying to pair up. So yeah, try and isolate those coefficients. But yeah, that was not trivial. Last part then. On the basis of the same calculation, the student guesses that all whole numbers in the range 1 up to a max appear amongst the coefficients for all positive integers k. Use part 2. Part 2, all right, that's our thing to do with a max, to show that they are wrong. Right, let's restate what we know about all of this. So what have we got so far? So we've got that a max is greater than or equal to 2 to the power k divided by n plus 1. So we've got that thing. We also know that the n plus 1 is the number of coefficients that we've got. So we've got that as well. And we also know that n is equal to k plus 1 over 2. So I'm putting that there because it kind of feels as though we're going to need to get all of this in terms of k rather than having n's there. That seems more likely because we're talking about all positive integers k. So it seems as though then, so if we've got all positive integers up to a max, then what's the highest? Well, the most we can get up to is n plus 1. If we've got all positive integers up to a max, then a max must be less than or equal to n plus 1, as that's the total number of coefficients that we've got. So that's summing. And 2 to the k over n plus 1 is less than a max. So we've got that on the other side. So we can then say, well, that's ruled out a max then. So we've got that 2 to the k over n plus 1 is less than or equal to n plus 1. And we know what n is. So this is leading to that 2 to the power of k is less than or equal to k plus 1 over 2 plus 1 all squared. Right, which do we want to manipulate that or not? Or is this just going to be, so what are we talking about? So use this to show that the student's guess is wrong. So eventually this is going to break down, and it hasn't broken down by the time we get to k is equal to 6. I mean, we can see this here. So if k was equal to 6, then we're getting 2 to the power of 6. So what's that, 64, which we're saying is less than or equal to 6 times 7 over 2, sorry, plus 1 all squared. So 21, 22 squared. Yeah, so that's definitely the case. But this is catching up, isn't it? This is catching up. Because, okay, it's all well and good saying that is 64, but then we take it up to 256 by making that an 8, and we'd have an 8 times 9, so we'd have 4 9s, 36 plus 1, we'd have 37 squared. So yeah, it's catching up. That's going to be the point. So as k goes to infinity, we'll have that 2 to the k. Well, the right hand side is going to tend to k to the power 4 is what we're going to want. It's going to be greater than k to the power 4, because that's what we're going to be left with as k gets bigger and bigger. The squared term is going to get swamped, and yeah, so we'll have k to the 4. So yeah, I mean, exponentials grow quicker than polynomials. So that's what we've got going on here. Yeah, even if you picked out 100 or something like that, it's going to already have overtaken. You can see how quickly this is catching up by doing this 2 to the power k. So you might want to say the exponential grows faster or something. Grows faster. Right, okay, so that last bit required quite a bit of detective work as well. I would say that was a very difficult question. The first part was easy. Part 2 was not too bad. Part 3 wasn't exactly trivial. And then 4 was difficult and 5 was difficult. So overall, I would say that was one of the more difficult questions. Obviously, it's personal taste with these sort of things. You know, there's some topics you like more than others, but that one I thought was not easy at all.